welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Ranjan Kumar Mallik. He will be speaking on signaling techniques for green communications. Professor Mallik is a professor in the Department of Electrical Engineering at IIT Delhi and a JC Bose National Fellow. He received his BTech from IIT Kanpur and his MS and PhD from the University of Southern California. He has previously worked at the Defense Electronics Research Laboratory, Hyderabad, and as a faculty at IIT Kharagpur and IIT Guwahati. His research spans wireless communications, space-time systems, cooperative and multiple access systems, power line and molecular communications, terahertz communications, and applied mathematics. He is a recipient of several prestigious awards, including the Shanti Swarup Bhatnagar Prize, the Khosla National Award, and the IEI IEEE Award for Engineering Excellence. Professor Mallik is a fellow of IEEE, TWAS, INAE, INSA, NASI, IASC, and the Asia Pacific Artificial Intelligence Association, and has served on editorial boards and technical committees of leading IEEE journals and conferences. Audience is encouraged to ask questions at any point during the talk. For those attending online, questions may be asked either by unmuting or speaking directly or by typing them in the chat box, from where they will be relayed to the speaker. Over to you, Professor.
Thanks for the introduction. Okay. So, the title of my talk is Signaling Techniques for Green Communications, and I'll basically speak mainly on receivers which do not need phase information. But before that, I'll just give the outline of my talk. So first, I'll introduce the basic topic and then delve into the system model. So we are talking of an n-branch receive diversity system with L levels of amplitude shift keying and one-sided ASK. That is starting, it could start with 0 or some positive value, the levels. It does not include both positive and negative values like is usually done for the coherent case, because it will not work for without phase information for the non-coherent case. Okay, then I'll go into the receiver structures and then symbol error probabilities, and then the optimization of the ASK levels, and finally some highlights of the performance of the different kinds of receivers. Okay, so as you know, modern communication systems have soaring data rates and huge energy consumption, and resulting in increased CO2 emission and related environmental problems. And to reduce this, we go into what we call the green communications concept. So you are basically environment friendly and try to consume less energy. So particularly it refers to the implementation of hardware or software techniques in the information and communication technology sector that aim to reduce energy consumption. And it's motivated by the need to mitigate environmental pollution and reduce economic costs. And these are some key technological aspects. One is cognitive radio. So this is used to effectively utilize the spectrum, basically. And then you have network coding, which is basically to use effective routing in networks. Then you have smart grid, where you have an electricity grid with advanced facilities of measurement, monitoring, protection, or you upgrade the present grid with those facilities, and so that you have more economy, security, reliability, and environmental protection. Then you have device-to-device communication. So it's a radio access technology that provides ability to communicate directly between users. Okay, and then you have the use of multiple antennas at transmitter and receiver. It's that is of course one of the forms. So basically you have both transmit diversity and receive diversity together. and it's normally called multiple input, multiple output, MIMO. And of course, if you have large numbers, it's called massive MIMO. And so, of course, you can have diversity in other modes like frequency or time, but we'll particularly focus on spatial ones, so which involves antennas. And they have advantages like good energy efficiency, robustness, enhanced throughput, etc. And finally, you have this concept of green IoT or Internet of Things. So it reduces the greenhouse effect and plays an important role by employing energy efficient procedures. Okay. Now, one of the key features that in green communications is that you want low complexity and low power receivers. Okay. And some of the applications which are of immediate concern are wireless sensor networks, then short range interconnects, cooperative communications, and some emerging technologies. Okay. And of course, support for IoT has also created interest in green communication. Now, one way to achieve this is by either you have fully non-coherent receivers which require no channel state information. So, no overheads in terms of pilot symbols to estimate the channel. You just know the channel statistics, or partially non-coherent communication. So, partially means that you do not have both the magnitude or the phase information of the channel. Typically refer to having magnitude type information. So, we will focus on magnitude and norm, but you are not bothered about the phase. So, that is also the reason why it is considered to be partially non-coherent. Of course, estimating just the magnitude information is much easier than estimating magnitude and phase together. So, that is the basic idea. Okay, so let us look at the system model. So, we we consider an n branch receive diversity system with L level ASK, and it is in flat Rayleigh fading. Okay. And of course, we are assuming equal a priori probabilities. So, your maximum likelihood receiver is the optimum. You do not need to go for a map receiver, and symbol by symbol detection, okay, not coded system. And if you bring the signals down to baseband and take sampled versions, then you can for the kth diversity branch, which we can visualize as the kth antenna element at the receiver. So, we have single antenna at transmitter and multiple antennas at the receiver. So, it is basically a SIMO system, single input, multiple output. So, RK is the received signal at the kth diversity branch, and it is HK times S plus NK. So, your HK is the channel coefficient or the random complex fading gain, okay, of the kth diversity branch, and S is the information bearing ASK symbol, and NK is the additive white Gaussian noise, okay, at the kth diversity branch. These are sampled versions of the time waveform. Okay, and due to Rayleigh fading, H1 to Hn are independent, identically distributed. So, we are considering IID Rayleigh fading, not correlated case. So, and they are complex circular Gaussian variables, each having mean 0 and variance sigma h squared. And the noises are having a variance of sigma n squared, okay, they are also IID. And of course, the channel coefficients are independent of the noise. That is generally implied, but still it's better to be explicit. And of course, we are talking of L level ASK, so S takes one of L levels from an ASK constellation. So, root E1 to root EL are the levels. We are using E for the energies, so root E will amplitude. Okay. E1 may or may not be 0. So, we will see that later, but definitely they are non-negative. So, root EI is the ith symbol amplitude level and EI is the energy level. Okay, and of course, without loss of generality, they are in ascending order. Okay. And of course, the probability, a priori probability is 1 by L for each. That is also already mentioned before, but still just mentioning again. And the average symbol energy is basically the arithmetic mean of the individual energies, which is sum of EIs divided by L, and the average signal to noise ratio per symbol per branch. It is basically the average energy times sigma h squared by sigma n squared. Okay, the ratios of the channel variance to the noise variance times the average energy. Yeah. So we call it gamma average, and gamma I is the ith SNR or SNR per branch of the ith symbol, the average SNR per branch. Okay, so it's EI sigma h squared by sigma n squared. Okay. And of course, because the energies are in ascending order, so are the gammas. Okay, the average SNRs. Fine. Now the objective of the receiver is to detect from R1 to Rn which of the LASK symbols is transmitted. Very simple digital communication problem. Now received signal vector is R, which is the column vector n by 1. So you have n branches, right? And the fading gain vector is h1 to hn stacked as a column. Okay, denoted as h. Okay, now we consider three kinds of receivers. One is the fully non-coherent receiver. So here it has knowledge of the n elements h1 to hn of the channel vector. It has no knowledge of the elements, and that is no channel state information, or rather no instantaneous channel state information. And it has knowledge of R, of course, it has knowledge of S, which is a constellation, what constellation you are using. And this is not a modulation classification problem here we are talking about. So it knows what modulation is used. And the statistical parameters sigma h squared and sigma n squared. Okay. The next one is the channel magnitude based receiver. So it has knowledge of the fading gain magnitudes mod of h1 to mod of hn, but not of the fading gain phases. Okay, angle h1 to angle hn. So it's partial channel state information, and it has knowledge of course, the R, S, and sigma h squared and sigma n squared. And finally, we consider the channel norm based receiver. So receiver has knowledge of norm of h, Euclidean norm of h. So that is root of mod of h1 squared plus mod of h2 squared, etc., up to mod of hn squared. It has no knowledge of the n elements h1 to hn individual, and that is again partial channel state information, and knowledge of norm R, and not of the n individual elements of R. And of course, it has knowledge of the constellation and the variances. Okay. So we'll just look at the receiver structures. So the first one is derivations are not this derivation is simple. So you basically have to find the PDF of R given S. That's it. You have to average over the channel statistics and the noise statistics. So the decision rule which turns out from that, the maximum likelihood receiver, and ML I refer to as maximum likelihood, which is the original unabbreviated form, not machine learning, which came much later. Okay. So this is basically the argument of the minimum of R Hermitian R is norm of R whole squared divided by a signal dependent scale factor plus a signal dependent bias, as you can see. Okay. So this is basically an energy detector. Why? Because norm of R whole squared is basically sum of mod of RK squared, and if you consider the time signal, it is integral of mod of RT squared dt, which is basically the energy of the received signal. Okay. So this is it's an energy detector, very simple. Okay. The simplest possible you can have. It requires only the knowledge of the statistics, sigma e squared and sigma n squared. Okay. I am, of course, here S squared is good enough. There is no need to put the mod, but just for notational clarity, I am putting it as mod of S. Okay. Because you are anyway considering levels which are non-negative. So, right. Of course, R is in general complex because you have the additive noise also. Plus you have the channel coefficient, which is complex. Okay. So that's the first receiver. This is basically under Rayleigh fading, okay, IID Rayleigh fading. This is optimum non-coherent receiver, fully non-coherent under IIT Rayleigh. Okay. Then the next one is the channel magnitude based optimum receiver. Yes. Yes. What closed form solution for? I mean, I have the closed form solution for the error probability. Yes, I'll show it later. No, S hat, I mean, you basically calculate the error probability, na? Simple error probability. Yeah, yeah. Yeah, I mean, you can expand. I mean, it is basically a search. You are searching over L levels, na? What you do is you just, you plug in the different values of S, na? You calculate L quantities, you see which is the minimum. No, 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 it's discrete. It is just ASK, na? They are ASK symbols. Right. So next is the channel magnitude based receiver. Okay. So here we have knowledge of basically mod of H1 to mod of Hn and mod of R1 to mod of Rn. Okay. And of course the channel statistics. So here this looks very different. So here it's you have to have the argmax of you have to take the natural log of this modified Bessel function of 0th order and first kind, and this is the argument of that, and then natural log minus you have a bias term. Okay. No, this is for partial CSI. This one, the previous one is full CSI. This is partial CSI. This is channel magnitude based. Na? So that is partial CSI itself. You are not considering the phase, that's all. Yeah. Okay. So now this one has high complexity. As you can see, Bessel function is there. So when you want to implement, you have to use a series expression with approximation. So and has implementation difficulty. Okay. And so what we go is for suboptimal, low complexity receivers. Okay. So we look at this is optimum, of course. Now we'll talk of two suboptimum. There are others also possible, but I'll just talk of two. So one is we call the weighted envelope detection receiver. Now how do you get the thing? It is simple. You know Bessel function I0 of x. For large arguments it is e to the power x by root of 2 pi x, right? So if you take the log, you'll get x minus half of ln of 2 pi x. So if x is large, then you can that ln term you can neglect. So approximately what you get just e to ln of that is approximately x. So the ln of this for large arguments, which typically will happen in a high SNR case, will just be this. Okay, ln of I0. So you get this minus this. So that is how you get this receiver. This is a WENVD receiver. Okay, this, and then you can rewrite this like this. So it is basically mod of Rk minus mod of Hks. So basically you just, it's like a least squares, least squares, you can call it estimation, but you are estimating discrete things. So you are trying to match mod of Rk with mod of Hks. In absence of noise, you will have an exact match, right? Of course, provided S is transmitted, exactly that the S which transmits will give you this as 0 when noise is 0. Okay. And you take the square and you add over all the branches. Okay. So this is argmin, this argmax becomes argin. There is a very easy to transfer from here to here. And if you ignore these are constants, right? So you can rewrite this one like this. So this is the WENVD receiver. Okay. This is again partial CSI based, channel magnitude based, but it's suboptimum. It's much simpler to implement, as you can see. Okay. Now another receiver which we'll look at is, it's the energy detection receiver. Okay. It's again partial CSI. So here what you do is you subtract mod of Rk squared. There you were subtracting between mod of Rk and mod of Hks. Here you subtract between the squares of them, and then take the square and you normalize by the channel coefficient squared, mod of the channel coefficient squared. Well, this is equivalent to this. You can easily show it. That's norm of R squared minus norm of H squared times mod of H squared whole squared, argmin. So you can simplify this like this. So this is the ED receiver or energy detection receiver. So, so essentially the easier way to remember is this one is here, this one, and the next one is this. They are basically least square type solutions. Okay. And now the advantage of the second receiver is that it is similar to the fully non-coherent receiver in structure, because you have the energy, you have a scale factor on the energy which is signal dependent, and then you have a bias. Okay, and the bias has basically the norm square of the channel coefficient. This actually is a channel norm based receiver only, but it's because if you look at it like this, you will not realize that it can be put like this straight. So, but fortunately, it is actually a channel norm based receiver. Okay, but we'll see channel norm based in a more general form. So, so this is another one. And you can easily switch if you have a hardware. In hardware, it is easy to switch between the fully non-coherent to this one. So that is one advantage. Because if you see here also, this is the bias, right? This is the bias, and you have this norm of R whole squared, and this is the scale factor. Yeah, here this is the bias, right? Of course, the bias depends on norm of H. There you don't have any channel state information. Okay, so now the next we go to the channel norm based receivers. Okay, so this is the optimum channel norm based energy detection receiver. Okay, now here what happens is norm of R is known and norm of H is known, right? And so this is how it looks like. So this is the modified Bessel function of the n minus 1th order in the first kind. Okay, so if n is 1, obviously it is 0, and this is how it looks like. Again, nonlinearity problem, so implementation is not easy. But there is one advantage here, because if n is large, okay, then what happens is you can use for norm of R whole squared, you can approximate to be a normal, because it is mod of R1 squared plus mod of R2 squared, etc., to mod of Rn squared, and they are all independent. So you can use the central limit theorem for large n. And so based on that, you can approximate to be a Gaussian norm of R squared. So if you take it as a Gaussian, to be real Gaussian, this is the mean, this is the variance, and you can get a Gaussian approximation. Actually, the Gaussian approximation is good for either large n or even for this condition. This is like high SNR condition. Okay, it's good for both. And this is the alternative receiver, but this is an approximation. So it holds only under those conditions. So this is approximation to the optimum receiver for channel norm based situation. Okay. This is also partial CSI, but even lower amount of information is required. Okay. Right. So this is simpler to implement, of course, but it has its limitations, as I said. Okay, now let's look at a suboptimum receiver for channel norm based case. Previous, yes?
What is this square brackets? Arg max?
Arg max, yeah. This
Term minus this term.
yeah, it's that, yeah, minus this, minus this. Yeah, yeah, it's not a matrix. No. It's just minus this. You can easily get from Gaussian statistics. See the log lake. Yeah. Right. So next is the suboptimum CNBED, the channel norm based receiver, which we call SCNBED, with parameter alpha. So this parameter alpha can be anything which is not 0. Okay, it can go from minus to infinity. Actually, there is no restriction, except for it has to exclude 0, nothing else. Okay, so here what do? We try to match norm of R to the power of alpha to norm of H to the power of alpha into mod of S to the power of alpha, and then take the square. Okay, so this is argmin of that, and this can be simplified if you expand. Okay, so this is how it looks like. So basically, it compares norm of R to the power of alpha to norm of H to the power of alpha into mod of S to the power of alpha. Okay. Now, when alpha equal to 2, we get the ED receiver, okay, because we have seen it was just norm of r squared minus norm of h squared mod of h squared whole square. So, that's a special case. So, but though ED receiver, it came from the channel magnitude based information, but then it could be equivalently put in this form. So, it actually satisfies both it is a channel norm based receiver as well as channel magnitude based receiver. Also, it depends on how you implement it. So, if you implement it in this form, if you implement in this form, it is obviously a channel magnitude based receiver. If you implement in this form, it is channel norm based receiver, or in this form. So, you could implement like this also without even simplification. It will work. Okay. Right. Now, these are some symbol error probability expressions. So, the first one is for the fully non-coherent receiver. Okay. So, here you have to use a CDF approach. So, basically their norm of r squared, which constitutes the decision variable. So, for different symbols you will have different types of gamma distributions, and the gamma distribution CDF has this kind of form as one of the terms. It is basically 1 minus basically it's 1 minus 0 minus x times summation, this kind of summation. Anyway, so these individual elements are parts of the gamma CDF, and this is the expression, and it basically depends on this ratio. This is the ratio of signal plus noise of adjacent symbols, as you can see. So, it's gamma I plus 1 divided by gamma I plus 1. It does not depend on distance between symbols. It depends on the ratios of signal plus noise. That is what happens in fully non-coherent case in Rayleigh fading. Okay. So, this is the expression, and it's a simple expression, gamma CDF type. Okay. It can be derived. It's there in one of my papers, the derivation. Okay. So, now for the WENVD, you cannot easily get a general expression because of the type of the expressions involved. So, what you do is you take high SNR approximation and you can get something. So, if you make an high SNR approximation, basically large gamma average and the first level 0 and the subsequent levels have large SNR. Okay. If you take that condition, then you can get this is the high SNR expression. It's also simple. Exact expression you cannot derive in the usual way. I do not know how to derive it. I have tried before. So, the best you could get is the high SNR approximation. Okay. So, this is for WENVD, which is again partial CSI channel magnitude based receiver. ED I will not go into separately because we will do for the other one for general alpha, and then alpha equal to 2 gives ED. So, we will not go into that right now. Okay. Now, under the high SNR condition, which is this one, that the difference of the gamma I plus 1 to gamma I, if this is large, along with this condition that this gamma is very large compared to n, or the first level 0 and the rest of the levels large compared to n, then you can approximate the optimum CNVD receiver performance also. You cannot do the optimum channel magnitude based approximation. So, you can use a Gaussian, but I don't have it here. I have it in my paper, and that's another paper, not the fully non-coherent paper. Okay. So, so we can approximate this and get this expression. This is also very simple. You see, this is actually the same as the coherent detection expression actually. So, but anyway, this also shows one more thing. We'll discuss the diversity gains later, but this it's clear that the diversity gain is n, here. So this is for the optimum CNBD. Then for the alpha dependent CNBD, which is suboptimum, this is the expression. So they basically, you have these two quantities, simple expression actually, algebraic, completely algebraic here. So this is BI, this BI term is twice like a modified mean of gamma I plus 1 gamma I. And on this, depending on BI and gamma I plus 1, you have these expressions delta I minus and delta I plus, okay? And in terms of them, you have this probability of error. They are all, you know, simple expressions, but of course, derivation is not that straightforward, but you can do it using, here the derivation is using a characteristic function approach of the decision variables. That's different from the CDF approach in the first case. Okay. So this is the expression. This is in closed form completely. Okay. Now, another important thing about this BI, which is, you know, this expression, as I said, it's something like twice the mean. So BI by 2 is basically between gamma I and gamma I plus 1. Okay, that is clear. But let's see what happens when alpha, how alpha changes. I mean, when alpha changes, how does BI change, BI by 2 change? If you take the, you know, extreme cases first, so for alpha tending to minus infinity, BI by 2 will be gamma I, which is minimum of these two. The other extreme is alpha going to infinity, it is gamma I plus 1 maximum. In between alpha equal to minus 2, you get the harmonic mean. Okay. Alpha equal to plus 2, you get the arithmetic mean. That's obvious. Now, what happens when alpha goes to 0? It's actually geometric mean. You can find out. You can find the limit. It is not obvious at all what happens when alpha goes to 0, but you will get the geometric mean. You can try it out. It's just an exercise in calculus. Okay. Right. Yes. Huh? Receiver structure. Yeah. Yes.
You said this is for high SNR.
Yes.
But that expression itself is for high SNR, right? So you're able to.
No. Expression is not for high SNR. That's a general receiver structure. Why for high SNR? What is for high SNR? I said the way it comes is, this is a suboptimum receiver. I am saying from the optimum for high SNR. I mean, if you consider high SNR, you can directly replace the ln I0 by the argument. So this is how it comes. You may be, but you can also think in terms of this. Na? That is not the only way. There is another way to think. See, the thing is that I am trying to match RK with mod HK times S, right? To get a suboptimum detector. So you can match it with any power, right? So here I have matched with the mod. It is not. It will be optimum for high SNR. That's all. But it is suboptimum. I'm saying, na?
Yes, but in probability of error expressions, you said high SNR. So
That no. But even then, you try to guide exactly, you will not be able to get it because of this mod of HK times mod of RK. You can't get it because of square hone se you can get it because you can use the characteristic function of the quadratic forms of Gaussians, but here you can't do it. That's the problem. Yeah, it will be root of quadratic form. It's a problem. Yeah. Okay. Forget it. I'm sorry. No, don't need to take the phone. Forget it. I should have put it silent. Don't bother. It will die out. Okay. Sorry. Right. So now for this, for this expression can also, it has a high SNR approximation which is used to get optimum levels for high SNR. So we'll see the high SNR approximation for this. So if you have BI by 2 minus gamma I very large and gamma I plus 1 minus BI by 2 very large, then we can get this high SNR approximation. It's pretty simple. Using this, you can get the optimum levels. So this is for the suboptimum CNBD receiver. Right. Now, let us look at some values of whether we can minimize alpha or not. There exists a minimum value of alpha uh, for this CNBD receiver, because that is that is one of the simplest which requires partial CSI. So this is we consider gamma average this like 200, which is basically how many dB? 23 dB, right? And this is for L4, these 4 levels, 4 ASK, and the the levels are basically actually the energy level differences, yes, the energy level differences are in arithmetic progression here. Anyway, so I've taken level 0, 1, 3, 6 here, of course with the proper scale factors so that you get the average the same, and this 200. And this is square, 1, 4, 9, 16 levels. And these are for various values of the number of receive antennas, 2, 4, 8, 16. And this is the high SNR, the minimum value of alpha when the SNR is high, which is obtained from this expression. And the exact one is the next one, which is obtained from this original expression, this one. Okay. So this is the actual alpha min. So let's see. First of all, of course, they are not, the SNRs are, this is like more asymptotic, but these SNRs are reasonably high, so they are close. These along the row they are close. Okay, but one thing you can see that it is not 2. I mean, it's close to 2, but it can deviate. Like here, it's 1.7. You can see. This is actual alpha min, right? Actual SNR dependent alpha min. So because the the logic is, why do we do all this exercise? So if you have a variable alpha and you can actually minimize the alpha and get best performance. So that's the basic idea. So this is one which gives a minimum SNR, minimum SEP. Sorry. Okay. So this one table for this is for L equal to 4, and this for L equal to 8. So here again you can see deviations from 2 as a minimum for these both. This is 800. This is more. This is 800 as gamma average, which is 29 dB. Right? Yes. No, no, no. This is dependent on gamma average, no? No, this high SNR one does not depend on gamma average as such. I mean, see, basically we are using this expression. It will depend on gammas, but what I'm saying is, we are using this approximation of the
But
SEP.
if you look at this values, if you could go to the table there. So you have like in the first part of the plot, you have 0, 1, 3, 6, and in the bottom you have 1, 4, 9, 16.
Yeah.
But like the alpha min value is not changing.
No, because the
much.
distributions are different, no?
Okay.
The gamma 1 to gamma 4 are different, no? Yeah, it will depend on so many factors. You see, this is just a trend. All that I am saying is that it is good to minimize the alpha to get a better performance of suboptimum receiver. See, if you can use the optimum receiver, that's the best, right? But when you want to simplify your receiver structure, when you go for suboptimum, at least some parameter you can tune to get a better performance, closer to optimum. That's all. That's what we are trying to do. Okay. This is for L equal to 8 again. Basically all that I am showing is they significantly deviate from 2. Actually, if you take lower values of n, I mean, we have taken n equal to 2, but if the gamma average is lower, we have taken sufficiently high gamma average actually. 29 dB, 23 dB is quite high. If you actually reduce the gamma average value, like if you take 18 instead of 800, you will get significant deviation. I have not shown that. Here I was just showing, it also shows that the asymptotic expression is reasonably accurate. That is why I took this high. Otherwise, you will get more deviation on this side from 2. Okay. So, of course, they both alphas increase with increase in n, that is number of branches, and they approach 2 as n becomes large. That is also true. So actually, if you take high SNR and n very large, then the optimum is 2. which will give you the minimum SEP. That is true. But every time you are not operating at high SNR, neither are you operating at large N, right? That is the most important thing to remember. Those are just limits. This is the problem when people get obsessed with diversity order, right, or diversity gain. Sometimes that diversity gain value is absolutely useless, even if it is high, because you will not even operate at the SNR. So it is actually, so because diversity gain is also easy to find, right? People don't even know how to find SEP, they just put outage probability and they get the diversity gain of that, which is actually not correct. Though there are hundreds of papers which do it. So it is wrong. So, but people do it because they do not know how to do it, how to do anything better. So, but it's a wrong concept. You have to use the simple error probability or bit error probability to get the diversity gain. And that too, diversity gain usefulness is questionable because you don't know how high is high when you get the slope, the almost linear slope in the log scale. Okay. Right. So for low and moderate SNR regimes and small n, the SEP minimizing values of alpha will deviate significantly from the value of 2. That is important to remember. Okay. So now let's look at level optimization. Okay. So we are basically minimizing the SEP either with respect to they're equivalent problems. Either you minimize with respect to gamma 1 to gamma L or E1 to EL, doesn't matter. Root of E1 to root EL. And subject to a, this is a total SNR constraint or a total energy constraint, and of course, they will be in ascending order. And the first level may or may not be 0, okay, but it will be greater than or equal to 0, right. So if you do that optimization, I will not get into the details. Of course, you can do it numerically using any standard mathematical package such as MATLAB. But the interesting results are that for the fully non-coherent optimum receiver, for high SNRs, actually the level should be, the first level should be 0 and the subsequent level should be in geometric progression, not in arithmetic progression. Actually, if you use arithmetic progression, it's a disaster. Okay. So, and if you have a common ratio. So, of course, you can calculate the common ratio, because if you know that you have a SNR constraint or a total energy constraint or total SNR constraint and everything is in GP, you can easily find out the levels. It's not a problem. The first level is 0. So there is no need to, the ratio can be easily obtained. Okay. Now, but so this is the common ratio actually in terms of E average. But it will be in GP. That's the most important result. And now for the WENVD receiver, it has a strange kind of progression. So this is this Ri is the ratio between not adjacent but alternate levels, gamma I plus 2 by gamma I. Okay, so that is Ri. So that ratio actually satisfies a nonlinear recurrence. Okay, of first order, starting with R0 equal to 1. So and the the levels root of first level is 0 and the subsequent levels are given in terms of RIs. You can easily calculate, once you know the recurrence and start with R0, you can calculate everything and all the levels in terms of E average, not a problem. Okay, this is WENVD. Now ED receiver is interesting. So here basically you have this is the expression that the difference between the energies will be in arithmetic progression. Okay, and so you can express the energy like this, the EI root of EI like this. These are the amplitude levels. But the bottom line is that the difference of the energies levels are in arithmetic progression. So will be the difference of the SNR levels. They'll just, it is a scale factor. The basic thing will not change. So if you have gamma I and this is gamma and this will be gamma average, that's all. There's no other difference. So symbol energy level difference is in arithmetic progression. So that's for the ED receiver. Now for the optimum, for the suboptimum BED receiver, we have this, not for the optimum. The suboptimum, this is the high SNR condition, okay, for the suboptimum receiver, for channel norm based receiver. And you also have to have the condition of large n, then you can actually get them analytically. So I mean, in terms of recurrence though, it's not an easy problem. So you denote these quantities gamma 1, rho 1 to rho L plus 1 as the ratios of the adjacent energies, gamma I plus 1 to gamma I, and you get this nonlinear recurrence in terms of when alpha greater than 2, you have this, you have to, you have these two, this is the starting equation to calculate rho 2, or rho 2 star, which is the optimum. This is a nonlinear recurrence. You can calculate rho 2 from here numerically, and then this is the, this is a nonlinear equation, and this is a nonlinear recurrence, first order recurrence, to get rho L plus 1 from rho L. But it's a nested recurrence, it's not explicit, like, it is not in the form of rho L plus 1 is equal to rho L, function of rho L, no. It's a nested one, you have to calculate from this. This is for alpha greater than 2. Okay. Now, if you, this is the best you can do, and interestingly for alpha greater than 2, the first level will be 0, the optimum, and the rest you can put in terms of rows, okay, like this. Now, when alpha is less than 2, the thing is the first level is not 0. That is the most important thing. When alpha is okay, then what happens is you have a, again you have these, this is a nonlinear equation to solve for rho 1, which is gamma 2 by gamma 1, right? And after that you have this again this nested recurrence to solve for rho L plus 1 in terms of rho L, okay, right? And then you can express the, so gamma 1 star will be this, it is not 0, and this will be gamma I star for the others. This for alpha less than 2. Okay, now this is a table just to show you how this rho 1 star varies for different values of alpha, alpha less than 2. So you can see that, this is alpha minus 4, minus 2, minus 1, it's gradually increasing. So it is this, and some of them can be actually lowered in closed form, like this one can be obtained in closed form. So I've just put them, this can be obtained in closed form, exact, in terms of this kind of number, irrational numbers. The others you have to do numerically. And as you can see, as alpha increases, this goes on increasing. So what happens is when alpha approaches 2, this is alpha less than 2, right? What will happen is it will ultimately at alpha equal to 2, it will go to infinity, which means gamma 1 is 0. Because rho 1 is gamma 2 by gamma 1, right? So rho 1 going to infinity means gamma 1 is 0. That means the first level is 0. That's what you are getting for alpha greater than 2. Alpha equal to 2 also, the first level is 0. Alpha less than 2, the first level will not be 0. But the ratio will become larger and larger, it will become smaller as rho alpha. Okay. Right. Now let's look at some features of performance. So now the diversity order of fully non-coherent optimum receiver is not that great, it's n by L minus 1, okay. So L equal to 2, you get full diversity order, which is n. See, the maximum diversity gain you can have for this system is n. But here it's n by, so if you use 4 level ASK, then you will get n by 3. You can't help it, even with the optimization of levels, everything, you can't do it. After all, you are doing fully non-coherent receiver with one-sided ASK, what else better do you expect, right? So you cannot, you should be practical in your expectations. So now diversity order WENVD, the interesting part is all these other receivers, WENVD, ED, the many of them. See, WNVD, optimum CNVD and suboptimum, all have diversity order n, full diversity order. So that is the main advantage. Okay. I did not calculate for the optimum channel magnitude based receiver, except for that I have, these are all calculated. So that is the biggest advantage, you can get full diversity order. Though general advice is not to be obsessed by diversity order, but still it's a parameter which many people are interested in knowing. So with partial CSI, you can get full diversity order, just like a coherent receiver. So of course, ED performs significantly better than non-coherent approaches, but it maintains a low complexity structure of non-coherent detectors. That is another advantage of ED receiver particularly. And SCP performance of ED receiver is much closer to that of a coherent receiver than to that of a fully non-coherent receiver. We'll see that in a plot. And optimization of levels has greater impact on the WENVD receiver than on the ED receiver, that also we'll see. Okay, so this is a plot of if you comparison of performance of 4-level ASK, optimum signal amplitude levels and signal amplitude levels in AP. So the reason why you need to optimize is this is here the optimum level. You see they fall, but you see the ones in AP they saturate. Why they saturate, that is explained in my paper, but they do saturate. Okay, so it's not good. So using arithmetic progression in non-coherent detection for Rayleigh fading channels is not good at all. You have to use geometric progression. Geometric progression is the quick one without optimization at all. You can use geometric progression and it is safe enough. Okay. Otherwise, you optimize the levels. Okay. So of course, when n increases, the performance improves. That is obvious. So I'll not. Okay. Now let's look at this is a performance of ED receiver. Okay, with symbol amplitude levels in arithmetic progression, coherent receiver, with symbol amplitude levels in AP and non-coherent receiver. This is symbol plus noise levels in GP. So this this is how it is. So this like for example, let's look at for n equal to 8. So this is non-coherent receiver. This is a non-coherent receiver. See, it does not look good here because you are comparing with better receivers. So this is the energy detection receiver, and this is a coherent receiver. Okay. See, the moment you compare with coherent receiver, obviously everything looks bad. So okay. So, but you see what I'm seeing. See, this is the non-coherent, and this is the partially non-coherent, and this is the coherent. So as SNR increases, this is much closer to this because this also has a falling curve, right? Unlike this, which is because here the diversity order we know, right? N by L minus 1, and this for L equal to 4. 8, sorry, that's the problem. It's N by 7, the diversity order. It's not good. But I just put, otherwise, these values, coherent value would be very low. If you put L equal to 4, it will be much lower. Because if you increase the number of levels, the performance also degrades, that we know. Okay. Now, this is the SNR gain, which is basically you keep this for high SNR. So, for high SNR, the SNR gain more or less flattens. So, that can be calculated, and for WENVD receiver, this is without optimization. If you use amplitude levels in arithmetic progression versus optimized levels. So, this is SNR gain, and for N, it's a bit looks complicated, but it's actually not that difficult. You can derive it. And if N is large, then what happens is I think this term will vanish. Only this is left. So anyway, let's look at numbers. So it's 2.5 dB for L equal to 4 and 4 dB for L equal to 8, less than 6 dB for large L. So it's significant gain. 3 dB is like twice, so it's not bad. Okay, so this is the plot of the SNR gain for L equal to 4 and 8. So this is for L equal to 4, L equal to 8. So increasing L, you get better SNR gain by optimizing. Okay, if you use more levels, then it's better that you optimize instead of just using arithmetic progression. Okay, right. This for WENVD, similar ED, it is a simpler expression. This is the SNR gain, and numbers SNR gains are not that high. It is 1.5 dB for L equal to 4, 2.2 dB for L equal to 8, and 3 dB for large. So this is the way. They are lower gains. So the advantage of getting, of optimizing is less. That's all. It does not mean that you don't get any gain, but you get less gain compared to WENVD. Okay. Of course, ED is also a simpler receiver, remember. See, the more simplicity you go to, then you will have to sacrifice in other things. WENVD is more complicated. So,
Why you are only looking after 15 dB? Why not? Because 15 dB, we are running in the minus I, right? This is good enough.
what? Where?
So,
Yeah, this is up to 20 dB. Just to show the relative things.
No, and last, next one, next, next, next. ACP you have calculated, no?
This is not ACP, this is SNR gain.
Figure 5. Figure 5.
Oh, I have not come to. Oh, this is. Uh, yeah, this is just you know, just a performance comparison. Yeah, obviously these values are very low, but
Because means
no, because I wanted to show the accuracy of the asymptotic optimal levels. That's why I
okay.
took higher SNR.
But otherwise, this is without obviously without channel coding, right?
Yeah, there's no channel coding here.
So then you can get another.
No, this just shows performance optimum CNBT receivers and coherent receivers, how close they are to coherent. That's all. So this for L equal to 4, 8, and 16. And then three types of levels are considered. One is coherent asymptotic optimal levels, then the asymptotic optimal levels. These are asymptotic optimal levels used for coherent detection, and this is asymptotic optimal levels, and this this is the optimum receiver, and this is the coherent receiver. So it is just comparing the optimum receiver with the coherent receiver. That's all. It is basically close. That's all I am showing, nothing else. For high enough SNR, it is sufficiently close to the coherent receiver. Of course, its alpha is equal to 2 has been taken here, but of course you could optimize the alpha also. This is for n equal to 10. That's why the values are also low. If I probably had lower value of n, it would be higher. This is of course numerically computed, not by simulation, that is clear. Otherwise I could not get with a normal usual computer. Right. Okay, now the next one, okay, this basically we first define the performance degradation, okay, in dB. So this is the probability of error of SCNBD. This is a comparison of SCNBD and coherent receiver, okay, coherent receiver performance. So if you have SCNBD with asymptotic optimal levels, and this is with coherent asymptotic optimal levels, okay. If you compare, this is the exact degradation dV, and this is the asymptotic degradation for n large, this is for n large, that's all. And the asymptotic performance degradation increase in L, and it reaches a minimum value of this 10 log of 12 plus 2 by 12 minus 1, which is basically, if L is large, it will be 0, right? How much will it be if L is large? It will be 0. 12 plus L equal to large is obviously not of interest. So L equal to 2, it will be 6 divided by 3, which is 3 dB. For L equal to 4, it will be 8 plus 10, 10 by 7. So 10 log 10 by 7. You have to calculate how much it is. This is for at alpha equal to 2, and then it increase in alpha. Let's see now the exact performance degradation follows similar trend. This is basically a plot of degradation versus alpha, degradation relative to coherent receiver. So you can see that the degradation is minimum when around 2. It's not exactly around, at 2, but it's around 2, the actual degradation. Asymptotic degradation minimizes at 2, not the exact degradation. Oh, sorry, it actually minimizes at this in terms of L, not at 2. It will be 2 for L equal to 2 actually. Yeah. So this is for L equal to 2, 4, 8, 16. So these are the plots. So what it shows is that If you want to operate, you find out, you operate at the one which gives you minimum degradation relative to coherent, because you always try to reach the performance of coherent, right? So, closer it the better. So, that is the basic idea, but it's not exactly always true. That is clear, but it hovers around 2. Okay, so now these are some of the advantages of using channel norm over channel element magnitudes. One is less computation complexity and allows channel estimation process to be simplified, and use of approximations based on central limit theorem. That is another advantage. You can simplify your optimum receiver in channel norm case. You can't do it for the others, for the other case. And these are useful for designing system in IoT applications, and of course CNBD approach is particularly suitable for IoT systems. Okay, and for high SNR and large N, the use of the suboptimum channel norm based receiver with alpha equal to 2 instead of the optimum channel norm based receiver does not incur much loss in performance. That is the advantage. And performance degradation of CNBD receivers when compared to a coherent receiver can be made sufficiently low by appropriate choice of parameters. That is also good. But and of course we have seen the diversity gain, right? It will have full diversity gain. So that these are the references. So the material is based from 4 papers. This is for the channel norm based receiver. This is for the channel magnitude based receiver and optimization, some optimization of the levels. This is the non-coherent receiver, complete non-coherent receiver. I have another further paper on channel norm with imperfect estimation, so using pilot symbols. I have another paper which appeared later. That I haven't covered yet. So that's it. Thank you for your patience, and questions are welcome.
Let's all thank this. Thank you very much, Professor, for a wonderful talk. So we request audience to ask questions if any.
Yes, Susan.
So, what kind of channel estimation algorithm you want to apply for this partial CSI?
Yeah, of course. I have used, I think in the paper, in the next paper subsequent to this channel norm, I had used LSE. But you can have better estimation. You can use MMSE, or you can. I mean, you can use either LSE or MMSE, or you can use statistics based, like you can use MAP or ML or MAP also you can use.
So then the question is that here, that if I use MMSC, then I can get the full CSA, right? So then why?
No, not necessarily. Channel norm estimation you don't. It is simpler. Okay. No, I don't have to use MMSE on the channel. I will use MMSE on the channel norm, na. Okay. See, yeah. Why will I? There's no need.
Yes. Okay.
Then of course things are much simpler. Yeah. Yeah. Once you estimate H1 to Hn, then you can use it. I know. Idea is not to estimate something. Yes, Sandra. Yeah.
For these receivers, you are essentially using knowledge of sigma h square.
And
Yes.
I mean the ratio basically. Yeah.
So if you were to ask what is a non-coherent receiver that is robust to channel statistics. So
that though you have to well,
among all distributions with the same sigma h square.
Normally, standard. See, the general concept of non-coherence is without instantaneous CSI. This without statistics.
Just using only second order statistics, but without the assumption of it being Rayleigh free.
Yeah, that's what you're saying, right? Yeah. That I have not thought of. Then, well, you can use if you have partial channel state information, you can. Well, if you have partial channel state, then obviously you have already too much information. It does not help. Yeah, that I have. but then the performance would be poor. That is so.
But you're not dependent on the channel being related.
Yeah, at all. Yeah, you're not dependent on channel statistics. Here I'm using channel statistics information, right? Because the moment you use a likelihood receiver or something like that, you're obviously using the channel. Yeah. Channel without like completely blind, right? Never thought of it.
I hope sir has answered all your questions. If you still have more questions or want to connect with Professor, please feel free to do so by having refreshments at the coffee hut. Thank you all and have a great evening.
Thank you.